Right. Well, thank you all for coming, and thanks to the organizers for graciously inviting me, even though I don't really do in a model theory, and let me just say, no mice will be iterated in the course of this talk, but I will maybe, if I have time at the end, raise some questions about consistency strength, which hopefully in the long run in a model theory can answer. But so really where this talk kind of has its start is back in the early history of set theory with a theorem by Hausdorff. So say that I'm going to try and write big so that I can be visible, if not legible. So a linear ordering L, throughout the talk, L is just going to be a kind of generic linear order. L is said to be scattered if the rationals considered as a linear ordering don't embed into L. And it turns out this is a very pleasantly structured class of linear orderings. So Hausdorff proved, remember this is quite early in the history of set theory. So the class of scattered, I'm just going to say lines as a shorthand for linear orders. So scattered lines, it's actually the least class containing, there are different ways you can say this. This is somehow the way that I prefer. Containing just the 1 point ordering and then closed under well-ordered and reverse well-ordered lexicographic sums. So if time is hanging heavy on your hands, you could try and prove this for yourself. I'll give you a clue that it's easy to see that the least class with these closure properties is contained in the scattered orderings. And then to go the other way, you take an ordering, you make an equivalence relation. We say 2 points are going to be equivalent if the interval between them is in this minimal class. And then you ask how many equivalence classes there are. But if there's just one equivalence class, it turns out that you're in this least class yourself. Any two equivalence classes have a class between them, so you very quickly embed the rationals. And from a kind of, a perspective which I don't necessarily think that Hausdorff had, this says that the property of being scattered is delta 1, hence absolute, right? So that if you're not scattered, that's sigma 1 because you embed a copy of Q, and that's upwards absolute. If you are scattered, you have a kind of certificate consisting of some kind of Borel code-like thing saying how you were built up, and that's absolute too. So, the received wisdom is to some extent, questions involving scatteredness are kind of immune to set theoretic independence as kind of an absolute class. All right, another definition. L is sigma scattered if and only if L's just a union. They can be disposed any old way of suborderings, Ln, and all the Ln's are scattered. And again, the theory of sigma scattered orderings, it's starting to get a little bit more set theoretic. But again, it's a very natural and pleasant class of orderings. And for example, Lever's beautiful theorem about well quasi-orderedness, the natural class to state Lever's theorem is to say that the sigma scattered orderings are well quasi-ordered under embeddability. All right, so far, doesn't seem to have very much to do with the kind of things that you probably associate with the kind of things I do. So what this talk is actually going to be about is about kind of non-compact objects whose cardinality is the successor of a singular. Okay, so now that's starting to sound a bit more like set theory as we know and love it. So here is a result by Todorcevic. It's in his book. It's in one of the later chapters, chapter 7 or maybe chapter 8. So if half kappa omega square kappa holds, there is a linear ordering L, cardinality L kappa plus L. I'm going to say this in a slightly deceptive way, but it kind of brings out the non-compactness rather clearly. So L is not sigma scattered, but every subordering is, well, it will be sigma scattered, but it's going to be even better. It's going to be sigma well-ordered. All right, so and the way I heard about this was okay, real talk, I didn't actually make it to chapter 8 of Stevo's excellent book, but Justin Moore pointed me in the direction of this theorem and said I should look at it. So Stevo's proof goes as follows. So, and I think I'm going to resist the temptation to get into too much detail at this point. So the way Stevo's proof goes is square kappa, you get a row function. The row function is kind of a generic term for the kind of things that Stevo likes to build by minimal walks on sequences of closed sets. So from the square, you can build a row function, which is a kind of very highly structured function from ordered pairs in kappa plus to kappa. So, yeah, some kind of pcf-theoretic scale, and finally from the scale you construct the linear ordering. Yeah, so this is what Justin told me about and said I should take a look at. So I looked at it and I thought a bit about what was going on, and I realized that actually you don't really need anything like in my theology, you don't really need anything like the full power of square sub kappa, and you don't need this intricate construction of the row function, that actually you can get away with much less. And so the picture, as I now see it, having thought about it, is actually there's going to be, just from again, it's important, as you'll see when I get into the guts of the proof, it's important that kappa is singular of cofinality omega. Okay, so I'm just going to take some old theorems by me and Matt Foreman and Menachem Magador off the shelf. So from weak square sub kappa, you can get a kind of a thing called a beta scale. If you know about good scales and if you know about very good scales, maybe it was an unfortunate coinage, the better scales are kind of intermediate between the good scales and the very good scales. Then we never gave this a name, but it's kind of a useful idea. From better scales happen to be what I'm calling today disjointing scales. And then you can just go straight from there to the kind of linear ordering. And this actually, this point of view, I mean, again, it fits very well into the kind of things I used to like to do with Matt and Menachem, where a big part of our project was replacing square-type hypotheses by hypotheses about scales in the hope of kind of isolating in a clearer way what was going on. So here there is some payoff in doing that kind of thing, because it turns out, I'm going to say this in maybe a slightly weak way, if kappa is alpha omega, I'm going to say it in a crude way, SCH fails at kappa. That also happens to get you, by an old theorem of Schaller, that happens to get you a better scale. So from the better scale, you can get the disjointing scale, and then you can get this. And when I write linear ordering here, I mean linear ordering just like in the conclusion of Stavos' theorem. So it itself is not sigma scattered, but every subordering is sigma well-ordered. Yeah, so again, it kind of fits into, fits into the worldview of people who care about compactness and non-compactness. That this kind of linear ordering, it has a property, namely in being not even sigma scattered, which is very different from all of its small suborderings, which are sigma well-ordered. All right, so let me see. I'm not sure which order to say these things in. So I think I'm going to try and get to the conclusion. I'm going to do the concluding bits first so that I don't run out of time. So let me just very quickly say, what do I mean by a scale? So again, just, scale is a pcf-theoretic concept which makes sense in great generality. The only kind of scale I care about here, I'm going to say a scale is, for my purposes, going to be given by the following data. I'm going to have each f alpha is going to be in the product of some cardinals kappa n, where kappa n are regular cardinals increasing with limit kappa, where the sequence of f alphas is cofinal in the product of the kappa n's modulo eventual domination. So these are kind of central objects in PCF theory, and probably the first theorem in PCF theory, proved by Schaller long ago, is if kappa is a singular cardinal of cofinality omega, then there is a sequence of regular cardinals kappa n cofinal in kappa, such that there is a sequence of f alphas of length kappa plus cofinal in this reduced product. Okay, so let's see. So in general, it can be a bit hard to get a good picture of what a sequence is doing if it's just increasing mod finite. But I'm going to say now, what does it mean for a scale to be disjointing? I'm going to say this sequence, f alpha, disjointing, it's got the following property, that for any initial segment, you can assign, eta, you can assign natural numbers to each index in an initial segment of your scale such that for all alpha beta, alpha less than beta less than eta, and for all m, what do I call them, n's, m greater than or equals n alpha n beta, actually f alpha of m is less than f beta of m. Okay, so the picture, it's not going to be a great picture, I'm afraid, is going to be something like this. The picture is on any initial segment of my scale, I can choose tails of my functions such that those tails are actually quite pleasantly organized. So, yeah, again, if you've ever seen the definitions of good scale or very good scale, you will see that they might have something of the same flavor. But here it's kind of a global demand. I want to say that actually on any initial segment, I can do this. Okay, so the reason that long ago, Matt and Menachem and I cared about these matters was if you take a disjointing scale, you could take the graphs of the functions in a disjointing scale, and that will give you a rather nice family of pairwise almost disjoint. It'll give you a family of kappa plus many pairwise. If you do a little bit of coding, you can cook up a family of kappa plus many pairwise almost disjoint cofinal subsets of kappa, such that on any small subfamily you can choose disjoint tails. And that is of interest if you care, for example, about stationary reflection, because the existence of such a family contradicts stationary reflection principles for stationary collections of countable sets. So, for example, if you want to see that weak square sub kappa kills stationary reflection for stationary collections of countable subsets of kappa plus, then that's a route to do it, is by way of this business. So, yeah, like I said, one weak square sub kappa implies the existence of a disjointing scale. So now, getting back to, at last, getting back to linear orderings, what we can do is, and again, you kind of recognize we're still in the world of kind of non-compact objects of cardinality kappa plus, but this property of being able to choose these tails, I mean, it's clearly a hopeless business to try and choose these tails uniformly, for all beta less than kappa plus. You're not going to succeed, basically because we're taking values in kappa. Anyway, yeah, so here really is kind of something that can be mined from Todorcevic's construction. So in fact, alpha plus is a disjointing now, and I'm just going to take that. I'm going to order it with the Lex ordering. And L is as required. So L is not sigma scattered. But it's close to being sigma well-ordered. Yeah, so something that was kind of giving me a headache when I started thinking about this is, yeah, the eventual domination ordering is rather different from the Lex ordering. And it would be quite boring if the Lex ordering could coincide. It would be hopeless for this purpose if the Lex ordering coincided with the eventual domination ordering. Because obviously, under the eventual domination ordering, these guys are just well ordered. So part of the trip is they're actually quite intricately ordered under the Lex ordering. All right, so let me prove this. But maybe let me digress. This is probably my most, any of my students will tell you, this is my most characteristic move, is to the instructive digression. So let's go back for a second to scattered and sigma scattered and the structure theory that Hausdorff gave us for scattered sets. So here's a fact. Let me call it lambda. If lambda is regular, uncountable cardinal, L is scattered. Ooh, that's sigma scattered, pardon me. L is sigma scattered, and the cardinality of L is lambda. And one of two things happens. Maybe they both happen. Maybe a copy of lambda embeds into L. So this thing here is the reversal. So if you're actually a sigma scattered ordering of some regular uncountable cardinality, lambda, then you yourself either embed a copy of lambda or a copy of lambda reversed. And this is a fun little exercise. So look, if L is sigma scattered, and has cardinality lambda, lambda's regular and uncountable. So my first move should be just isolate inside L a scattered subordering of size lambda. And then I've just got to prove that every scattered ordering of size lambda either embeds a copy of lambda or a copy of lambda star. And that's a fairly straightforward induction on this Hausdorff structural picture of how a scattered order is built up. So, well, on level 0, you're just a point, but then you don't have cardinality lambda. On level 1, you're either an ordinal or a reversed ordinal, and you're in excellent shape. And then you just keep going by induction. So the point is that, let's see, where was I going with this? So the point is that I want to prove that L, which has cardinality kappa plus, is not sigma scattered. If it was sigma scattered, it would have to embed a copy of kappa plus or the reversal of kappa plus under Lex. But proof, L has a dense subset cardinality kappa. Okay, I don't want to get bogged down in that. It's kind of a detail. It's rather easy. What I'm going to do is I'm just going to take for each finite sequence in the product of the kappa n's up to some finite point. Maybe it's an initial segment of f alpha for some alpha. So if it is, then I choose it, and then I argue that that's a dense collection. So the point is, L has a dense subset of cardinality kappa. That implies, for sure, kappa plus and kappa plus reversed don't embed into L, and that implies L is not sigma scattered. Okay, so that's half the battle, that L itself is not sigma scattered for, in fact, it's got this much stronger property of having a dense subset of cardinality kappa. So now I want to kind of do the other side of the coin. Maybe Staber's theorem has been up here long enough. I want to argue that the small suborderings are all sigma-well-ordered. The way I do that now, how am I doing for time? How many minutes? Okay, great. So for the other bit, I'm going to say it's going to be, for the other half, it's going to be enough to show that for every eta less than kappa plus, the collection of F alpha less than eta ordered by Lex is sigma-well-ordered. But that's actually surprisingly easy, knowing what we know, because remember, my hypothesis is that this is a disjointing scale. So I'm going to choose some integers witnessing the disjointing. Here's n beta. So, and then I'm going to say F beta and beta equals n. This is actually well ordered by Lex. And the reason it's well ordered by Lex is that if I have two things in this class, then actually I know, if I have two distinct guys here, I know that one of them eventually dominates the other, so I know that they differ eventually. But actually, I know more in this situation. Since if I have two guys, beta and gamma, and n beta equals n gamma equals n, then I actually know that f beta of n is going to be less than, I suppose, f gamma of n. So now the point is, now if I map f beta maps to f beta restrict n plus 1, this is going to be less than Lex order preserving map into product over, let's see, I'm running out of good letters. What did I say? N. I guess m less than equals n kappa m under Lex. But this actually is a well ordering, right? It's just the Lex ordering on a finite product of ordinals. Okay, so this thing here is well ordered. Okay, so that's the gist of it. So I think maybe for the rest of this talk, let me kind of show my hand a bit more and say maybe more explicitly what the squares have got to do with anything, and maybe what is this betterness of which I spoke. Okay, so maybe I'll say what is very goodness first, and then maybe I'll kind of fall back to betterness. Okay, so again, so as above, so once again, f alpha, the scale, we're going to say then f alpha is very good if and only if for all eta less than kappa plus cofinality greater than omega, there is C contained in eta of, there is, let me say, n less than omega, such that for all alpha beta in C with alpha less than beta, and all m greater or equals n, f alpha of m is less than f beta of n. Okay, I'm the first to admit that there's a lot of quantifiers in this. So let me draw a picture. Picture is worth 1,000 words here. What am I really saying? I'm saying I can identify this club, and inside this club, I can identify these tails in a uniform way. And these functions are literally pointwise increasing on these tails. Okay, so and now it so happens that, so this comes from those old papers with Matt and Monaco, square kappa implies the existence of a very good scale. And again, I don't want to belabor the point, but the rough idea is something like this. Shell tells you that there is a scale, and now what you're going to do is you're going to use that scale as a template to build a very good scale. And the coherence properties of the square that you started with are going to end up with this. So I don't want to say too much about this. Let me just say the following. Because kappa is singular, square kappa can be witnessed by a sequence where all the order types are strictly less than kappa. So if you're in the business of building, and there's some inductive hypothesis, which I'm not going to tell you, but if you're in the business of building inductively, kind of using any old initial scale as your guide, you reach a limit stage eta of uncountable cofinality. You take the club C eta, which you are given by the square, and you look at the order type of C eta, which is dominated by kappa n for some sufficiently large n. And then you start taking some pointwise soups of the functions that you built so far up C eta. And like I said, there's an induction hypothesis, there's some coherence, but at the end of the game, what comes out is a very good scale. And when I was looking at Stevo's book, at this point, this is when I had a kind of shock of recognition, because from the rho function, Stevo constructs something which appears to be a very good scale with extra bells and whistles coming from the subadditivity properties of the row function. Seems like a very interesting combinatorial object, but I haven't thought about it as hard as I'd like to yet. Okay, now, what is a beta scale? Beta? Okay, it starts off the same way. So for every eta less than kappa plus, half eta greater than omega, there is C contained in eta club. Okay, but now there's some kind of quantifier switch going on. So what it's going to be is actually, I'm going to say it in the most uniform way possible. For every eta in C, there is an AM for every alpha intersect eta F. Maybe let me, for uniformity, say F alpha. Let's think F for okay, so somehow things are just organized a little bit differently, that you don't quite have the kind of uniform lockstep. I think since life is short, I'm not gonna try and draw the picture of the beta scale. Two things I am gonna say about beta scales. I think I mentioned this already, but now you can prove it for yourselves. Beta scales are disjointing, and actually, if you've ever sort of messed around with this kind of combinatorics about, I don't know, ladder systems that live on non-reflecting stationary sets and choosing disjoint tails of ladder systems for non-reflecting stationary sets, then you'll recognize that argument has a lot of DNA in common with the proof that a beta scale is disjointing. And the other thing, other facts that I can now quote from the paper, weak square kappa implies there is a beta scale. And to forestall the obvious question, or maybe a couple of obvious questions, actually, if you know Ernest Schimmeling's hierarchy of intermediate weak square principles going between square kappa and weak square sub kappa, actually quite interestingly, weak square sub kappa lambda for any lambda less than kappa is good enough for a very good scale. Weak square sub kappa is not good enough for a very good scale. Again, because of some reflection type principles. Very good scale actually rules out some amount of simultaneous stationary reflection, which is compatible with weak square. More of the stuff in our old paper. Let's see. So, in the last few minutes, that's most of what I wanted to. That's most of what I wanted to say about these matters. Except, yeah. Let me just say how this works. So now the idea is. You're trying to build a beta scale, but now you've only got a weak square sequence. And a weak square sequence at each relevant eta, instead of handing you a single club C eta, hands you a family of kappa many clubs. So what you've got to do is for each useful member of that family of kappa many clubs, use it to compute a pointwise soup of what you did so far. That's a family of kappa many functions, but the original scale that you're using as your template, has order type kappa plus. So you can find something which eventually dominates each of those pointwise soups, and that tells you how to continue. But the price you pay is that you got this kind of quantifier swap in the kind of increasingness of the scale. All right, so the way this business, which I think is intriguing, and again, I haven't thought about it enough, the way this business with failure of SCH at Aleph Omega goes is, suppose SCH fails at Aleph Omega, well, then by more PCF trickery, you can find a sequence of Aleph ends such that there's a scale of length Aleph Omega plus 2 in their reduced product. And now, well, but you don't have any real, you don't have any even weak square, but you have what Sarah likes to call the silly square. You have the principle which hands you at each eta less than Aleph Omega, hands you Aleph Omega plus 1 many clubs in a kind of coherent way. Okay, mostly silly square is silly, but actually, since the sequence of functions that I got from the PCF trickery, is actually an increasing Aleph Omega plus 2 sequence, having Aleph Omega plus 1 pointwise soups and then dominating them all is enough. So that's how that works. And then finally, okay, I'm veering off the topic of my talk just to try and say something that has got some vague connection with my talk and also some vague connection within a model theory as I understand it. These are questions I'd really like to know the answer to. Is how does the consistency strength of the failure of square kappa for cof kappa equals omega, how does it compare with the consistency strength of the failure of weak square? So that's my kind of question. So cof kappa equals omega, compare strength not square kappa not weak square kappa. So a very nice theorem by Martin Zeeman, which says you can actually get the failure of square at a point, a cardinal of cofinality, omega, from something below kappa plus supercompactness. And so what Martin's theorem is, if kappa is both measurable and subcompact, so subcompactness makes square fail, and after doing prickery, or really anything kind of vaguely prickery-like at kappa, after prickery, kappa, square kappa fails. And to my knowledge, though hopefully there's someone in this crowd who can tell me different, but to my knowledge, if you like to get the failure of weak square sub-kappa in this situation, you seem to need something on the order of kappa plus supercompactness. Maybe you can fudge it, but I don't know how to fudge it. And like I said, so somehow, in my mind, these hypotheses are very different because I guess subcompactness is witnessed by some family. Well, I guess obviously measurability is witnessed by a measure. Subcompactness is witnessed by some family of kind of super strong type extenders. To me, that has a very different flavor from the kind of extender that's witnessing the supercompactness. And that's a piece of mathematical gossip, which again makes me wonder about the relative consistency strength of PFA and MM. So now I can show PFA is consistent with every lambda. Actually, I'm going to say in full ignorance, PF is actually consistent with the version of weak square where you have LF2 clubs at each level, and you can have that for every lambda, whereas MM implies not weak square lambda. And you can say a lot more along these lines. MM actually kills so-called good scale, which is a much weaker principle than a very good scale. So somehow, so for the purposes of this flavor of singular cardinal combinatorics, somehow PFA looks very different from MM, making me, it is true, by the way, I mean, Stavo's proof really shows PFA does actually kill square lambda LF1, but it happens to be consistent with square lambda LF2. So somehow, it seems like the received wisdom among this crowd that PFA and MM both require a supercompact cardinal, but somehow in my mathematical world, they look kind of different when you get up to their influence on singular cardinals. Okay, I'm going to stop.